like known to take the stage and you can use the same for this.
I'll try.
Okay. This please hold on. Sorry.
Good morning, Professor Jen and audience. My name is Non Kittanon Tenriaden, and today I'm going to defend my master thesis in the topic of deposition and characterization of DCMS or direct current magneton sputtering niobium titanium nitride superconducting thin film for SIF clarity. It's one part of such a work. And here my overview divided in 6 parts. Start with introduction, what is SRF clarity and how it developed, and then we will come to the substrate preparation. In this thesis, we prepare 2 substrates. One is silicon, and secondly is the copper. The third one, I will tell you what the PVD machine that we use and how to vary our parameter. And then after we coded, we will go to the characterization method, how we analyze our samples, and then we will go into the result and discussion. And lastly, I will conclude all again the result. Let's start with what is RF cavity. RF cavity is the metallic chamber that imputes the energy by accelerating the particle inside the cavity by electromagnetic field. Mainly made of the bulk copper. Problem by the bulk copper is the high electromagnetic resistivity and make a lot of energy loss. Then bulk niobium SIF cavity is introduced. Compared with the bulk copper, bulk niobium show high Q factor. What is Q factor? Q factor is the factor indicate the energy storage. And here produce can minimize the energy loss. So coming the third one is the better performance of EACC. EACC is indicate the factor indicate the accelerating gradient inside the cavity. However, the bulk niobium SRF cavity also show the limitation. One is poor thermal conductivity, secondly is the neat cryogenics process, and the third one is limit operating temperature at 2 Kelvin. So we're coming into our work. On the right hand side, we roll back to copper cavity, but with a superconducting thin film on the surface. We also know that copper cavity have one advantage as a good thermal conductivity. So, and we can deposit with a wide range of material like niobium, niobium nitride, niobium titanium nitride, and niobium aluminum. So that we can improve from this thin film by the TC or superconducting property around 16 to 18 Kelvin, and we compare with bulk niobium only 9.2 Kelvin. And then we can also improve the operating temperature around 4 Kelvin. And then we coming to the method. The method that we use for my master thesis is DCMS or direct current magneton sputtering. When compared with the conventional CVD, we can expect high deposition rate, and we can deposit with diverse range of target material with DCMS. Moreover, with DCMS, we can reduce the scattering effects and enhance the mean free part of the ions. In addition, with the DCMS, we have a plasma ionization zone. That means we can do with the high beam, and that creates a superior thin film. For the thin film that we use in this master thesis is niobium titanium nitride thin film. For copper SI cavity, when we have mainly for apparently advantage. First one, the TC superconducting property around 16, that more than 9.2 from bulk niobium. Second one, we can also improve the SRF gravity and enable the lightweight of SRF gravity. And with this thin film also offer the robust mechanical and chemical stability. And the fourth one, we also have the main advantage is we can find the optimal superconducting and structural property by parameter, control the parameter, sorry. Now, the purpose of my master thesis is to find the optimal niobium titanium thin film which is appropriate for copper SIF gravity. Now, we coming to the next part is sample preparation. As I also mentioned before, 2 samples were prepared, start with copper. In the copper, the polishing, we start with mechanical polishing, and then we did electropolishing after that. For mechanical polishing, the objective for the mechanical polishing is to suffer imperfection removal. We got at first the copper substrate in square shape, 25 times 25 millimeters, millimeters, and then we polish with the 3-5 grade of sandpaper, start with 1,200, 2,500, and 4,000 micron with the water as a lubricant. And the last step for mechanical polishing, we polish with the 3 micron diamond suspension. However, the micro scratch and the contaminant also stay on the copper surface. That means why we have to do the electropolishing. For electropolishing, divide into two subsets. Firstly is for the clean the copper surface, start with in ethanol for 15 minutes in ultrasonic bath, then still in ultrasonic bath but in acetone. And then we will activate the copper surface in aminosulfuric acid for 5 minutes. While we clean and activate the copper surface, we will prepare the electropolishing station. Start with the electropolishing solution. Here, the blue one consists of the phosphoric acid and butanol in the ratio of T/2. And then we will heating up with the heating plate until the thermometer temperature reaches 40 degrees. And then we will move our copper after activate the copper surface as far as we can into the lead cam as an anode in the direction of facing the glass wall. And then for the cathode, we will put the bulk copper into the cathode and we will turn on the DC power for electropolishing for 40 minutes. Now we get coming to the silicon. For the silicon, we got firstly with the silicon wafer at the left hand side pictures with 10 centimeter diameters. And then we will cut the silicon wafer into square shape with 2 centimeter times 2 centimeter. However, after we cut the silicon, we will still got a contaminant and residual silicon. So we will put the cut silicon into the outer bar for 5 to 10 minutes in ethanol for clean and rinse with distilled water and dry with drying nitrogen gas. Now, both samples are ready, so we will put both of them into the Chemicron Industrial PVD Coating 2 CC800. For this PVD Coating 2, offer like object control, and we can in real-time monitoring for the deposition process. And if you see on the left-hand side, the middle one, you see the substrate holder that we will put all our copper and silicon inside on it. On the opposite side of the substrate holder, we will see like the target. Mainly target that we use in Chemicon is aluminum, titanium, and niobium titanium alloy. But in this study, we use only the niobium titanium alloy in DC mode for deposited. Now, coming to the experiment hand, here in this master thesis, we vary 4 main parameters. Start with series 1, varying the position pressure, coming to with power cathode in series 2. For series 3 and series 4, we vary negative substrate bias in high pressure for series 3 and in low pressure for in low pressure. For the last parameter, we vary nitrogen concentrations ratio in working gas ratio in high pressure for series 5 and in low pressure for series 6. Now we coming after we deposit, we will characterize in 4 main methods. start with XRD or X-ray that for crystallographic analysis and to predict the lattice parameter and the grain size. For the roughness analysis, we will use AFM, and for analysis for film microstructure, surface morphology, and cross-section morphology, we will use SAM with high resolution image. For the last one, for TC or superconducting property, thank you for our partner, Group of Surface Theory and Superconductivity, Survey INFM, Lake Naro, National Laboratory, Italy. They did for us. Now, coming to the result and discussion, start with the effect of varying deposition pressure. What we see from the left-hand side, from the low pressure range, 0.7 Pascal until 1.1, and from high pressure range, 1.3 to 2 Pascal. We got it from the XRD result. From copper, we will get two mains reflection, from 1-on-1 reflection and 0-2 reflection on the left-hand side. At low pressure, from 0.7 to 0.9, we will get the result from 0.02. In the other hand, for the high pressure range, from 1.3 until 2 Pascal, we will get the result from 1-on-1. And however, when we focus on the 0.2, the reflection of XRD, we will see that the peak, the middle peak, also like on the right hand side shifting. That means we will see the two theta shifting right and on the right hand side. And what we got analysis from here, the trend, we will get that with the higher pressure, the grain size and the lattice parameter will be decreased. Now coming to the surface analysis, here I still divide in two parts at a low pressure range and high pressure range. At low pressure range, we got so smooth the surface with irregular shape. In the other hand, at high pressure range from 1.3 to 2 Pascal, we got uniform pyramidal shape. And with higher pressure deposition, the microstructure will be more compact to each other and more pyramidal shape. For the cross section, here in all pressure case, we got all columnar structures. And at low pressure, columnar will be the trend for the columnar will be the thickness will be decreased, and for the high pressure, the trend of the thickness will be thicker. Here, it shows the conclusion again in the part of varying deposition pressure. We see the thickness of the pressure still decrease, while for the high pressure increase around from 788, 1.3, and end up at 989 at 2 Pascal. For the roughness RQ, when we got from RQ in both range, like the factory, that is still unclear for the roughness. Now, coming to the superconductivity of varying pressure, we start at TC at 14.42 at 0.5, and when we still increasing, the TC is slightly decreased. What does it mean? That means that the optimal superconducting property require operate at low pressure ligament. Now, coming to the second parameter is varying cathode power. If we see on the XRD result, we will get the reflection both 1-on-1 and 0-2 reflection. But in this case, I predict both of the grain size and lattice parameter from 1-on-1 reflection. What we got when we zoom in the 1-on-1, we got that with higher cathode power, we got higher peak and narrow peak to each other. And that's still constant in the middle, that means no shifting occur in XRD reflection. And what we got from analysis on the right hand side, we get that analysis at higher cathode power, the grain size on the orange curve, on the red curve, will be increasing, while the lattice period tended decreasing. Now, coming to the surface analysis of cathode power, all of these cases show like the pyramidal grain growth. That means, but when increasing the cathode power, that show more pyramidal grain growth due to enhanced atomic energy and during depositions. Coming to the cross-section analysis, what we got here still all columnar structure, but with the film thickness increasing. Here show more about the conclusion of the thickness and roughness for cathode power. That I told before, that thickness is 10 higher, started at 387 nanometer and slightly increasing 600, 708, and end up at 960 at 451. For the roughness of we got Lafner when we increase the cathode power, start at 10.3 and end up at 20.3 at 450. Now, coming through the third parameter, start with the symmetry in high pressure. What we got here from the XRD reflection, we will see that, at the negative low bias, 0 and 50 volt, we will get the result from one reflection, while for high negative substrate bias in 100 and 150 volt, we will get the result from 0.2. And if we zoom in from 0.2, we will see that, the peak will be in the left-hand side shaping. And what we got from analysis showed that with higher negative bias in high pressure, the grain size at the blue curve will be the grain size as a red curve will be decreased, while the lattice parameter still increase. For the surface analysis in high pressure, we saw it's apparently for the low substrate bias 0 1 and 50 1 we got like pyramidal shape, while for 100 volts and 150 we get irregular shape. What does it mean? That means that increasing substrate bias we got smoother surface and more compact denser grain due to higher positive ion flux to the substrate. Now coming to the cross section of substrate bias in high pressure, we got in this case still in all columnar structure with the thinner thickness trend. Here show again the conclusion of the thickness and the roughness substrate in high pressure. What we got the thickness exactly decreasing, starting at 969 nanometer at slow 1, still decreasing and end up at 642 at 150 volts. For the roughness, it's still better. We start at slow 1, 25.3 nanometer and still decreasing 28, 15 and end up at 5.1 at 151 substrate bias. Now we're coming still in the substrate bias but in low pressure for CD4. What we got from XRD? We got XRD only from 0.02. And if we zoom in the 0.02 reflection in the length line, we will see that the peak still almost constant. That means no shifting of XRD reflection. And what we got from analysis, when we increasing substrate bias in low pressure, the grain size as the red curve tends smaller, while the lattice parameter as blue curve tends constant around 4.38 or 4.39. For the surface analysis in low pressure of negative substrate bias, we got in this case so smoother surface with irregular trend, and with increasing substrate bias in low pressure, we get smoother surface and more compact denser grain due to higher positive ion flux to the substrate. Now coming to still, but for the cross-section analysis, we got also all in columnar structure with the thinner thickness trend. Here show the conclusions of the substrate bias in low pressure. We saw so thickness still decreasing, and while for the roughness still increasing. We got roughness when we increasing negative bias in low pressure. Now show superconducting activity of varying substrate bias. If we hold the pressure constant both in high and low, and we adjust only negative bias, what we see that TC will be increased when we increasing the substrate bias. And when we hold the substrate bias constant, maybe at 50, we will see that at low pressure, we will get higher TC than on the high pressure. That means that superconducting property require operation at low pressure rate requirement. Now, coming to the last parameter, varying nitrogen gas, start with in high pressure range for CD5. What we got from XRD analysis, we got almost 411 reflection. And when we zoom in from 411 reflection, we will see that, that's almost constant in the middle. That means no shifting of XRD occurs. And what we got from analysis on the right hand side, with increasing nitrogen percent, we got the smaller gain size as the red curve, and the lattice parameter almost constant at around 4.337 until 4.339. For nitrogen gas in high pressure, we get the surface analysis or pyramidal shape, but with increasing nitrogen gas ratio in high pressure, we got more permeable grain structure and more compact grain. For the cross-section analysis, here still, all of this case, we got also all columnar with a thinner thickness trend. Here show the conclusion again with the thickness and roughness, but in high pressure range of nitrogen gas ratio, the thickness still decreasing because of we increase nitrogen gas, that means we decrease the argon ratio or sputum gas. For the roughness, we got smoother, start with 20.5 at 5% and 20, that means first time increasing and still slightly decreasing 17.9 and 15.9 at 20%. Now we're coming to the last theory, but still in nitrogen gas ratio in low pressure range. We are also, what we got from XRD. XRD result show that we got the result only from zero slope 2. That means all the lattice parameter and grain size were predicted from zero slope 2 reflection. And if we zoom in and focus on the red line, we will see that, oh, the middle peak still fast constant. And with higher percent in low pressure, we will get lower peak of XRD result, but wider. And what we got from analysis on the right hand side, we got that all the grain size as the lake curve tendly smaller, apparently smaller. However, the lattice parameter tendly increasing, just only once from 5 to 9% increasing and slightly decreasing. For surface analysis, because in low pressure, we got all here irregular shape with the smoother shape. And with increased nitrogen gas ratio in low pressure, it's still irregular shape and but smoother surface, smoother grain, sorry. And for cross-section analysis, what we got still all columnar structure, but with increasing nitrogen gas ratio in low pressure, the thickness is thinner or decreasing. Here show the last conclusion tables of nitrogen gas ratio in low pressure range. The thickness trendy apparently decreasing, and for the roughness, we got smoother surface with the higher nitrogen gas ratio in low pressure range. Now, we're coming to the superconductivity of varying nitrogen gas ratio in both high pressure and low pressure. For high pressure, if we increase N2 ratio, we will see that Tc will decrease. This trend will also occur in low pressure at 0.9 Pascal. When we increasing, Tc will decrease. And when we compare with the same N2 ratio, at this case maybe 9, we will see that Tc from low pressure is higher than Tc from high pressure. What does it mean? That indicates that high superconducting property require operation at low pressure range requirement. Now coming to the last slide, conclusion. From my master's thesis, we can conclude from 4 different parameters varying with 5 conclusions. With higher diffusion pressure, that show is the decreased Tc with increasing roughness. For the cathode power, when we increase it, we got roughness surface but higher Tc. The same result occur by increasing N2 ratio in both high and low pressure range. That means we got roughness surface but higher Tc. The interesting is the increasing substrate bias. The increasing substrate bias in low pressure will be enhance both Tc and the roughness. However, increasing substrate bias in high pressure increase Tc but decrease the roughness, or we got smoother surface. What does it mean? Does mean this synergistic effect suggests substrate bias in high pressure may be produce the optimal niobium titanium thin film with higher Tc and lower roughness. So the table below show 3 samples with the three highest Tc. Start with DC, niobium titanium nitride 24 at 14.85. However, the roughness is still high at 27.9. For DC, niobium titanium 26, we get the second highest Tc at 14.43, and with the roughness just only 5.1, so smoother surface. And if we indicate that from the Tc and the roughness, DC niobium titanium nitride 26 show the most optimized thin film for copper SRF gravity. Thank you for all your attention.
questions or any discussion? One, so you're welcome, particularly these two, Sasha and Professor. So you have to evaluate then the master thesis of Kittenon.
But it's a part of something.
Yeah. Could you please go to series 1 deposition pressure experiments?
Disposition pressure?
Yeah, I think series 1, I guess.
The first one.
XRD graph, yeah.
This one?
Yeah. So why do you have less intensity of that niobium titanium nitrate with the 200 orientation is lesser for 1.1, 1.3, 1.4? Is it? Did you really get very low intensity of that? Did you not equalize the y-axis properly?
I mean, it's depend on. Yeah. I also discussed with him, Sasha, for the reflection. It's depend on like the lattice parameter of this copper surface. And when we compare, we have already converted both of from 111 and 002 in macro Excel. And it's truly exact like more precision when we use like for low pressure for 111 because of the convert the grain from the peak, right? And with the higher like this, we got almost nothing from the reflection. That means better we calculate from the with the acrylic peak better.
Okay, so you did not get any peak.
We got a peak. We got a peak, but too slow.
Very less intense.
Yeah.
Really?
Yeah.
Yes, maybe I just can add. Yes, so first, when I saw this, I also thought that could be some issues with the axis normalization or whatever. But if you look closely to some small reflection on the right hand side around this 200, yeah, you see this small thing?
So this one.
No. More next.
Next.
Oh.
Silicon peak.
No, this was deposited on copper. So and this is XRDs on samples on copper, and this you see it's a copper reflection, and for copper there should be more or less the same.
Yeah.
And this 200 really so high intense. So once I even tried to do pole figures from such samples, and it's like was really oriented into 200. Yeah. So this is really, and this is log scale. I mean,
Yeah,
the
that's
real even higher. So this is.
Yeah. So did you measure TC values, the films that are deposited on silicon or copper?
Oh, we did in all my cases, only on copper.
On silicon, right?
On copper. Only on copper. That's why I focus on only 111 and 002 reflection. Yes.
Anyone
I
else?
see.
Okay.
We have one small question. In your presentation, you highlight the surface runnings will have influence to the superconductor property.
Do you mean TC, né?
Yeah. Could you explain the reason?
This one?
Why the surface runnings?
Okay.
Surface runnings.
Surface.
Yeah.
Reference.
Roughness, né?
Yeah.
Okay.
This one has influence to the superconductor property. Why? Reason.
I mean, I found this information from the research. Mainly, I think I always in my master's thesis also indicate that in general when we make like indicate how to for superconducting property for the material, this depend mainly from two parameters, from TC, from superconducting properties and the roughness. And for the smooth, for transfer the energy, we need like some kind of the smoother surface and higher TC.
So as the figure 6.7, this one? I'm sure there's no. 6.7. picture. B.
High bias picture.
You
In-
separated.
Yeah. High bias pictures. Maybe this one.
No.
The surface analysis.
This one is it?
Yeah.
You may see the series,
Ah,
which
okay.
series.
So it's the upper right.
Yeah.
This
01, 51,
this
100, and 150.
I mean figure B.
Figure B. Yes.
If you look it carefully, you can find something.
I mean, first, I think I saw one thing that I saw the elongate of the grain and almost in two reflection. You see when we consider the direction of the grain, we get some kind of like this and like this. And
you see the morphology, right?
yeah,
The lower left, you have some homogeneous region, and the right upper
In-
left
yeah.
is
like it depends on I think from the grain reflection, maybe from the direction of the grain. I mean 1, 0, 2 something. In the another
I mean,
orientation.
this is very small area, right? This is some
Yeah.
maybe show some influence of the substrate structure.
Yes, for sure. Mainly, I think when the reason that we start with the deposition pressure, we got apparent.
This copper, no? This
Yeah,
is-
copper.
this is I mean, this is maybe show some influence of the copper.
In my opinion, maybe from the parameters, because of we normally when we consider from the Sasha, we have 5 parameters like the substrate temperature. But I think here is only we don't vary the substrate temperature. And for this one,
I mean, I don't mean the substrate parameter is some structural characteristic. Maybe you have some grain
yes.
under this area, which has influence on the orientation of the crystal.
Okay.
I mean, you get the point.
Yeah, you mean we
You
get
see
different
you
of
see
orientations.
two different
Yeah, two different direction of the grain.
direction of
Mhm.
the crystal lines
Mhm.
for such small region. So this is not a factor of the experimental parameter. I mean, the only difference could be the underlying substrate.
I'm sorry, I'm not sure, but in my opinion, I think it depends on like the we deposit on the copper, right? And this depends on like the tension or compress like residual stress of the surface. Maybe show off the surface like this.
Anyhow, this is some arrangement.
I'm not sure, but also I'm not confirm.
So this is at a high pressure, right? So what is the pressure here?
1.8 was
1 point.
1.8 was.
So do you have at low pressure one?
Yes.
150. Yeah, I think you have it right.
This one.
Yeah. So here did film break or something at 150? Like overall, if you look at the film, okay, I think on copper it is difficult to see, right?
Yeah,
Even
difficult to
if
see.
the film
Difficult to see. But one thing that I discovered him at low pressure, our copper, like the thickness, we will have like the different orientation because of the tensile and the copper residual stress on the film. Yes.
Can you go to cross section of it? I think you have taken it from silicon, right? So this means that I think it did not break at 150 volts substrate bias, right? So the cross section looks pretty good. I mean, it's
Yes,
very
yes.
uniform and- Yeah.
But I think it's depend on the technique that I use. Sometimes we got like so apparently picture, sometimes it's like real pictures. And maybe you are right, maybe not, maybe yes, I'm not sure. Because of the pictures.
Because yeah, sometimes if it breaks, you can't even see such kind of thing actually, cross section. What happened at 100 volts? It looks quite. The delamination happened, right?
This depends on the process from the person picture, from the person below.
How did you prepare this cross section?
Cross section, okay, because of we need cross section and we deposit on the silicon, and then we cut the silicon
This one is
from silicon. That's why we prepare copper and silicon for this synthesis.
No, this is up to 0.5 Pascal.
0.5?
What is the pressure here?
0.9.
0.
0.9.
Nitrogen concentration, how much?
We hold around 9%. 9%,
9%.
yes. We hold 9%. We vary only one. From this case, is only negative substitute.
I mean, why do you have like larger thickness for 150 volts compared to the magnification is same for all?
No, sometimes I want like some kind of the apparently pictures. That means sometimes we got 44K. Sometimes we got only like this 25K. That's why you
Okay.
see the thing differently.
No, but you should have kept like the same magnification, like same scale for everything, right?
Okay,
So then
that's
we
for
can
my-
compare.
my error.
Yes, yeah, that's right. Yeah.
Or you could just measure, that
Uh-huh.
this one is this much.
That's why you look differently from
Yeah.
slow mo and apparently different from other ones.
In this case, then, why would you then at higher pressures see at high bias, negative bias, let's say smooth surface without such effects of delamination or cracking of the film, but at low pressure you could, or you may observe such things?
Like I mentioned before, I think at low pressure we got some kind of the more resistance rate, more resistance than in high pressure. That's why we got the delaminations or something like this.
Why?
And tension compression as a
Yes, but what the origin of such things?
maybe from respiratory.
Yeah.
Yeah.
You must have asked him before.
I asked him before, but I know.
But you
Yeah,
forgot
from
that.
respiratory.
Anyone else? So, non, well done. Congratulations to you.
It was really good time.
Lily?
Yes, yes.
I'm so nervous.
And now our third presenter, Mr. Gu, so he will present, so last for today. So don't worry, huh?